just plug in x squared instead of x and see what we get there. Okay. And then the last part, we want to find the radius of convergence. Same process here, right? So you're going to take the what's it called? The ratio test. Sorry, I had a little brain for this. So take the ratio test. So ends up being same process that we did in the last example. So quickly, a sub n plus 1 is negative 1 to the n, and then x to the 2n. I'll put this in parentheses here because it's going to be a little different. Like that. Okay, so this is technically 2n plus 2. Again, that's going to be a little important right now. Okay, so this is going to take the limit as n goes to infinity of this whole thing. Again, this doesn't matter because it just, it's absolute value. So again, this is going to be n to the 2n times x squared, right? This is plus 2. Divided by n plus 1 times n factorial. And over here, everything flips. Oh. Okay. And again, things cancel, which is what's all important about this stuff. So we get the limit of n goes to infinity. And this is just x squared, so x squared is always positive, so just x squared over. And the only thing we have n plus 1. Oh, what am I think I messed up here. Oh, this is why it doesn't look right to me. This is not n factorial, right? Yeah, it's not. Okay, that makes a huge difference. Very, very sorry. Okay, that changes everything. Okay. Okay, so that's going to be limit as n goes to infinity of, this is still there, so it'll be x squared on the outside and over n plus 1. There we go. That's what it should be looking like. Very, very sorry about that. And this goes to 1, so it is just x squared. Okay. Now, according to the ratio test, right, in order for this limit to converge, it must be strictly less than 1. So we know x squared must be less than 1. So going backwards, we're taking the square root of both sides. X must be bounded between negative 1 and 1 to be convergence. And there we go. All right, let's try another one. All right, x cosine x. Now again, going back over here, we know what cosine is. So the only difference between what we have here and what we're looking for here is just by multiplying by x. So literally, we're just going to multiply every term by cosine x by x. So if I go over here, I'm just going to times this by x, times by x, times by x, times x, and so forth down the line. So this ends up being 1 times x is just x minus x to the third, because this x squared times x is x to the third over 2, plus x to the fifth over 4, and it keeps going. This one's factorial, right? Yeah, this one's factorial. So in general, it is literally just cosine, but multiplied by another x value. So let's do exactly that. So this is the sum of n equaling 0 to infinity of negative 1 to the n times x to the 2n times another x all over 2n factorial. And again, you're perfectly fine at this point, but if you look at your back of your book, they'll put these together to make it look like this. And there you go. Either one's fine. Okay. And then finally, find its radius of convergence. So I don't have too much little space here, so I'll just put an extra piece of paper on here. And so again, I'll just write down what a sub n is plus 1 is going to be. Again, I'm not going to bother with that because they're taking the absolute value, so I'll just go over here. So this will end up being x to the, looking like that on top. And looking like that on the bottom. Okay, so again, doing the ratio, taking the limit as n goes to infinity. And again, I'm going to slowly break this up. This is, if I distribute 2n plus 2 plus 1, so that's going to be 3. So this could be x to the 2n times x to the third. And over here, if I distribute, this is 2n plus 2 factorial. Okay. So this is going to be 2n plus 2, 2n plus 1, and then 2n factorial. Okay. And again, the reason why is because, let me go back over here. It is 2n factorial, so it's not just 2 times factorial, it's just collided together. So you just got to be a little bit careful about that concept there. Okay. Okay, so that's on that one, and on this one is exactly this. Keep doing that. And I don't know why I did that, but it's fine. I'll just put that there. Oh. Okay. So this ends up being the limit as n goes to infinity of just x squared times 1 over 2n plus 2, 2n plus 1. And again, this goes to 0. Okay. Now, unlike the other one, where I had the radius bounded between 1 and negative 1, let's go back over here. So like I said, the ratio said it has to be bounded between negative 1, and the reason for that is because if you look at our template one we had on example 3, natural log has a radius of 1, so it had to be bounded between 1 and some value. Here, however, if you go to cosine, the radius is infinite, right? So therefore, if you multiply by another number, in this case just x, it literally does nothing, right? If it already goes to infinity, so if I multiply by, in this case, 2 times it, oh, sorry, yeah, 2 times it. Let's see if I go, sorry, very, very sorry. If I just square it, it's really not going to do nothing to it, right? I'm just squaring an infinite number, which just gets more infinite. So therefore, in this case, the radius is also infinite. So when it comes to the finding these convergence, you know, not only you have to verify it because of the ratio test, you also have to verify depending on the the template you used in this case. So since our template in this case was going to infinity, it really didn't matter what we multiplied. But again, you still got to make sure that's actually true itself. Okay. So let's try the last example here so you can kind of give the estimation how we did it. All right, now let's look at C, a little bit more space here in this case. Okay. All right, so for C, we want to find its series of divergence and Maclaurin series of these two things, e to the 3x minus e to the 2x. Okay. Now again, we have a template for that-ish, right? We have e to the x. So, if you guys agree, the only difference between e to the x, let's say the first one, we'll just look at the first one, is just 3 times x on top. So therefore, guess what we're about to do? Everywhere we see an x in here, we're now going to substitute 3x instead. And that's pretty much it, right, when it comes to it. And same thing over here. Everywhere I see an x, I'll now substitute 2x instead. So really, if I rewrite this now with its respective forms, instead of this now, all these x's are going to be 3x's, and then it's going to be all these x's with 2x now. So it's going to kind of look like this. So that goes on, and then minus this series, which is 1, and I'll just put this in parentheses, right? 1 plus, and again, it's going to be the exact same thing, except now it's just going to be 2x instead. Okay. So notice the only thing that really cancels from one to the other is 1, right? Everything else, well, we'll put these together. 3x minus 2x, we can put this minus that, so forth. So you can kind of tell these cancel, that cancels, and you just get x plus 3x squared minus 2x squared, and this is supposed to be a 2. 3x to the third minus 2x to the third, and so forth down the line. Or, if we do this each individually, try to make it a little nicer to look at. And just running with its respective power series, that's exactly it.